Hi, welcome to our lecture on continuity, lecture 11. So we've discussed limits, and now we're finding a use for them. Continuity is an important feature regarding functions. You could think of it as the ability to draw a graph without lifting your pen or pencil. We're going to get into a bit more of a technical definition, which coincidentally involves limits. We say a function, call it f of x, is continuous at x equals a, so some particular x value, if the following three conditions are met. The limit as x approaches a of f of x exists. Okay, good to have. Number two is like it. F of a is defined. These first two are really just set up for number three. Three is the most important one, but you do need these first two. So the limit exists at that point. The function is defined at that point when x is a. And then the main part is that the limit is equal to f of a. So this third point is the heart of it, but the first two conditions are needed to get there. So in other words, the value we approach, that is the limit, is the true value of the function. At x equals a. So the value we approach, which is the limit, agrees with how the function truly behaves there. So no sudden jumps like we saw in the previous lesson. So if a function is not continuous, if not continuous at a point, we say it is discontinuous. And again, we're talking at a particular point for now. For example, I'm going to draw something that looks like the absolute value function. Here's x, y. Let's draw a couple points. We're going to draw a hole at 1, 1. Okay, and besides that, looks like the absolute value function. But at x equals 1, the true function value is down there. It does a sudden jump. So in this case, focusing on that x value of 1, the limit as x approaches 1 of f of x, and yes, this is a graph of y equals f of x, Well, the limit is 1 because that is the y value that we're approaching. That's what matters when it comes to limits. However, the true value f of 1 is not that, it's 0, height 0. So because you have this disconnect, this is discontinuous at this point. So we say f of x is discontinuous at x equals 1. So that's using a graph. Let's deal with an expression. Again, we're focusing on discontinuity at the moment. Find all values x equals a. So by this, I mean particular x values. Where f of x is discontinuous. So where we fail to be continuous. And here's the function. So to be discontinuous, you need any one of those 3 conditions we mentioned to fail. So if you can find a place where the limit does not exist, great. If you find a place where the function is not defined, great, you're discontinuous there. Or if perhaps the limit exists and the function is defined, but there's a disagreement, like we saw in the previous example, then also you're discontinuous at that point. It helps to break down this f of x. This is factorable. Factors like that. And that's often going to be the trick when you see a rational function like this. Factor, and we see that there's some cancellation. We need to be a little bit careful here. This means that this function is equal to x plus 4, but with a small condition. This is true as long as x is not 4 itself. So it looks like this x plus 4 everywhere, except you're not defined when x is 4 because of that original expression. You're technically dividing by 0. So if you were to graph this, it would look like this line, y equals x plus 4, but you would draw a hole here when x is 4. So the function fails to be defined there. Let's say f of 4 does not exist because of that original denominator. So we are discontinuous. At x equals 4. Your graph just has a hole in it there. Notice that everywhere else is fine. X plus 4 is a perfectly well-behaved function. It's just a line, so it's continuous everywhere except for there. So Now, talking about a function more broadly, a function overall is continuous, so this is something new. We're not just talking about continuous at a point, but just the function is continuous itself if it's continuous at every point. Let's abbreviate that. So if your function is continuous at every point, you just say the function is continuous. And a good rule of note, which can help, is that polynomials are always continuous. So when you're doing a problem like the one we just did, and you get here with your function, that's a polynomial, except we're just saying we're not defined at that point. Well, everywhere else you're continuous because polynomials are always continuous. So that's a useful fact. Now, for a challenge problem, we want to find some number k to make g of x continuous. And here's g of x. We're going to set it up as piecewise, just defining it in separate parts or pieces. So this is going to be a rational function for this part. X squared minus x minus 6 over x minus 3. And the function looks like this everywhere except when x is 3. So our function is basically this, except at this particular point. And when x is 3, it's going to look like this, kx minus 5. So k, this is what we're searching for. We want to find that value k, which will make this thing continuous. So continuous at every single point. The problem point is 3, you can tell. Right, that's the only issue we run into in this rational function because of the denominator. Everywhere else is fine. So 3, that's the real sticking point. Now, what does it mean to be continuous again? Is that the limit as x approaches 3, in this case, that limit exists. F of 3 exists. That would be whatever this is when we plug in 3 for x. And most of all, those two things have to agree. So the limit must agree. Now let me say the limit as x approaches 3 must agree with the actual function value at 3. So the value your function is approaching is the same as the actual function value, so no sudden jumps, essentially. Well, let's calculate that limit. That's perhaps the hardest part. Oh, I'm sorry, I wrote f of 3, that's supposed to be g. We're using different letters for this problem. There we go. So the limit of g of x as x approaches 3. So which of these two expressions will we use for that? Well, it boils down to the fact that our function looks like this rational function, almost everywhere, except when x is 3. So when x is 2.99999, we would plug that x value into this. Likewise, if x is 3.000001, we plug that into this expression. So that is what determines the limit, because that's what we use when x gets very close to 3. So I might as well just plug in this expression here. This is what matters for the limit. Okay. So the same trick as before, this thing factors. All right. And you can see it becomes x plus 2, x minus 3. That does the trick. And that's convenient, right? Because these cancel. So this is equal to the limit as x approaches 3 of plain old x plus 2. Remember, we saw a little bit ago, this is almost equal to the expression we had before. It's just that you're missing that point when x is 3. Technically, you have a hole there, but I can say that these are equal because we're talking about limits. So the limit is still the same. You know, this x plus 2 is almost the same thing as this expression we had. Just a hole at x equals 3. Well, when you're looking at the limit, that doesn't really matter. So plug in 3 now. The limit is 5. So when my x values get very, very close to 3, my function g is approaching the y value of 5. And to be continuous, we want this to be equal to the actual literal g of 3. So g of 3, pardon my scrolling. Well, this tells us what we do when g is actually 3. We use this expression. And so we plug in 3 for x. So instead of writing k times 3, I'll just write 3k. Looks a little nicer. So that is 3k minus 5. So we set this equal to 5. That comes from this 5 up here. The limit. And then we solve for k. That's the point. Is we want to find a k which makes this function continuous. That means that the function value is the same as the limit. So we add 5 to both sides. And k is 10 thirds. See you in the next lesson about rates of change.